In this session of programming and automation for geoscientists, we'll start working on mapping with GMT, the generic mapping tools, and its Python interface, PyGMT. The question that we want to ask is how we can automate making publication quality maps, XY plots, and even animations using world-class base data sets while having maximum flexibility regarding the layout of our products. And the answer, certainly in the geophysics world, to this is using GMT, the generic mapping tools, and more recently, the Python interface or API that has been developed, PyGMT. So PyGMT expands Python and brings GMT into the Python world. We'll talk about what GMT is in a little bit here. PyGMT brings together decades of work on mapping in the Unix and Linux world that is captured within GMT and moves it into the Python world that we are all quite familiar with. GMT itself is an open source collection of command line tools to make maps and to manipulate geographic and Cartesian data sets. There's a lot of filtering, trend fitting, gridding, projecting, and other functionality that is available within GMT that is otherwise complicated to implement yourself. So even if you don't need GMT for map making, there are a lot of useful tools available for you that can make your data analysis a lot easier. So once the data analysis is done, it allows you to produce high quality illustrations from simple XY plots through contour maps, artificially illuminated surfaces, and 3D perspective views. There are many different map projections and transformations between them included. And what is extremely useful are the databases it comes with that include coastlines, rivers, political boundaries, down to country and county polygons. It also provides topography, bathymetry, age of the ocean floor, and other very useful data sets in high resolution that can contribute to your data analysis or to your data presentation. So this is one example. This is a map of the topography of the Earth. And with GMT, you can make this entire map with one command. Here's the command. This is on a command line. The prompt is indicated here. We call GMT, we use the module grid image. We want to show the Earth relief in 10-minute resolution. We want to use a region that is global. We want to have illumination that is default. And we want it to be a PNG that is called world map. Now, I don't expect you to understand these command line arguments or to remember them even. I very frequently have to consult the vast documentation for GMT to ensure that I understand how to visualize the thing that I'm interested in. The key point to make here is that I didn't have to manually download that data set for the topography myself. GMT did that for me. All I need to know is how to tell GMT to get me this Earth relief in this resolution. We could also use a coarser or finer resolution. GMT documentation provides you with the resolutions that it has available, and you can interpolate if necessary, or GMT does that for you. A map of the globe in one step. Here's a more complex example where we have a map of the ocean floor with some track lines across here that cross a mid-ocean ridge that is highlighted by this blue line. Up top, an XY plot that shows the depth of the bathymetry versus the distance from the ridge. So you can see here in gray the stacked profile, and in black we see the median of this. This is done entirely with GMT. This is an example script that is available on the GMT website. If you were to engage in shell scripting with GMT, this is what your scripts would kind of look like. We don't expect you to do this here in the course. We just present these examples in the background so you understand the philosophy of GMT and can utilize it through the PyGMT API yourself. So what's going on? First, we start a session, GMT begin, and we call this, the output for this is going to be called example 33. And each line does a specific thing. For some of those, there are comments here. So the first line calls GMT to grid cut. This should look somewhat familiar. Now, this is a 1-minute Earth relief resolution in a region that is specified here. So go from 118 degrees west to 107 degrees west. So this is this extent. And from 49 degrees south to 42 degrees south. So we're going from 49 to 42 degrees south. So this region string here just tells GMT what the area is that we're interested in. And then it makes a grid. So -G is save the output of this command to this file that we call spac_33.nc. And grid cut will now download Earth relief in 1-minute resolution, focused on the region that is specified here, and then save in that output file. Next, we make a color palette. So GMT make CPT is make color palette. We want a color palette that uses the default scheme that is called rainbow. There are many default color palettes available, but we want to scale it from -5,000 to -2,000 meters. That's what the -T does here. And then we plot it. GMT grid image takes this East Pacific Rise grid file that we saved. We give it some illumination that is at an azimuth of 15 degrees. And we use a Mercator projection, -J term here. We give it some matte frame using the defaults. Next, we select 2 points along the ridge. We're taking this longitude and this latitude and this longitude and that latitude and put it in the file ridge.txt. Cat reads from the command line until an EOF shows up, which is a marker that is shown down here. And it reads this line, and then it sees EOF and it stops. So it takes that input and then redirects it into ridge.txt. All you need to know is that ridge.txt contains those 2 points, which are equivalent to these endpoints on the East Pacific Rise. Now we plot the ridge segment and the endpoints. First, we're using GMT plot to plot a line, 2-point thick and blue from the beginning to the end of these points. And then we use plot, and we plot little circles that have these dimensions. They should also be blue, and we plot them on top. And now we have the blue line with those blue circles up top. The reason to show this is so you understand that within GMT, there's a lot of layering. You start out with a base data set, and then you might want to add some points or some lines in relation to the base data set. If we were to draw the blue line and those points first, and then add the bathymetry, the blue line would still be there in those dots, but they would be hidden underneath the layer of the bathymetry. So if you were to open this PostScript or PDF file in Illustrator or Inkscape, you could remove these layers and kind of uncover or reorder them. Whatever you plot is going to be on top of all the stuff that you plotted before. So if you plot something that is non-transparent or covers the entire image, it's going to cover everything up that was there before. We're using grid track along the ridge coordinates, give it the bathymetry to create 400 kilometer long and 10 kilometer spaced cross-profile lines across here. Save these to table.txt. Now we're plotting table.txt, so we add these black lines up top here. And now the trick happens. We're next plotting this upper XY plot. The key command line argument is this -YH plus 3 centimeters, which shifts the output of this command 3 centimeters further up. And so we create a subplot. The subplot has a new region. It goes from -200 to 200. So we are abandoning the previous region that was specified up here, which was the region within which all of these other commands operated in. So instead now we go from -200 to 200 on the x-axis and -3,500 to 2,000 on the y-axis. We also use a new projection, XY projection, which should be 15 centimeters in the horizontal and 7.5 centimeters in the vertical. Our pen should be 3 points thick. We plot the stack file that came out of the grid track in light gray. Next, we plot the base map, which doesn't have anything to do with the data that is already plotted, but helps us to determine the spacing of the grids, spacing of the tick marks, where the labels for the tick marks should be, adding the X and the Y axis labels. So this first B is turning the X-axis, add labels every 100 kilometers, and label the entire thing distance from ridge in kilometers. And then for the Y-axis, we're just adding depth label here and use the default spacing. We also want more labels to show up on the western side and on the southern side, but not on the north and eastern side. This is what this command here adds. Lastly, we give it some coordinates, which is 0 here and minus 2000, which gets us to this point. We pipe this string into GMT text, which then centers it in a 14-point font on that location and gives us a nice header for the median stack profile. Last, there's just some deletion of temporary files done. We end our GMT session and we show the result. This is a really compact example of a complicated analysis that can easily be done with the available data that come with GMT. You could do that anywhere. This isn't going to take a half hour to put together. Usually GMT plots take me, depending on how complex they are, anywhere between a couple of hours to a day or more. So this is something to be expected, but you're not just making a figure, you are presenting data, you're going through the processes of data analysis here. You're oftentimes revising how you're going to be presenting what it is that you want to show. And you will consult the documentation a lot to understand these fairly cryptic command line arguments and make sure that you use them in the right way so that the plot ends up looking the way that you want it to. But you have incredible control here. There are people who use GMT to make their entire scientific posters. GMT was initiated in 1987 at Lamont by Paul Wessel and Walter Smith, who were graduate students at the time and needed a better tool to plot data and make maps. It started out as a set of Unix command line tools that made PostScript. And PostScript is a page description language. It tells the printer what to do, how to take an image and turn it into a printed page. GMT evolved through many major versions over the last decades, now provides shell script, MATLAB, Python, and Julia support. It all kind of sits on a common GMT API, application programming interface, that is written in C and C++. And the GMT on the command line that we just saw in these examples is leveraging that API. The Python API is leveraged by PyGMT, and then there's MATLAB and Julia. And all of that sits on top of system libraries that provide a lot of general functionality. We've seen a very simple and a more complex example. GMT can solve a lot of simple problems directly as one-liners, but the real strength of GMT comes from the ability to layer data and add multiple plots, which was the second example that I showed. This is realized via the GMT sessions. Remember that GMT begin, example 33, and then a bunch of stuff happened. And at the bottom, there was GMT end and show. And all of this is best implemented in shell scripts. So I would recommend to anybody who is doing plotting with GMT or PyGMT, build these maps up step by step. Start out with the topography or background that you want to have, and then add one layer after the other. Do not try to do it all at once, because then you'll have way too many issues to fix.